This is Chapter 4, Differential Relations for Fluid Flow, Part 3. In this video, what I'm going to talk about is the derivation of the differential equation for the fluid acceleration field. And we're going to carefully distinguish between local and convective accelerations. We've encountered this before, this concept before, when we talked about a Venturi tube. We know that in a steady flow you can have fluid accelerations. So imagine flow through a Venturi tube where the pump is delivering a constant volume flow rate. We know that the flow accelerates as you move towards the throat of the Venturi tube because of the decreasing cross-sectional area, and then it decelerates as it moves into the expansion section. So fluid acceleration does not require transient flow. So we're going to derive the expression for the acceleration field in differential form, and then I'll show how to express it in vector notation. And I'll end the video with a couple of mathematical examples. The first is calculating fluid acceleration in a steady flow in a nozzle. So we'll deal with those convective accelerations that I just mentioned. And the second example is calculating the acceleration field given a mathematical expression for the velocity vector field. All of this discussion is vital background for the next video where I discuss the conservation of linear momentum. What we're going to discuss in the next video is basically F equals ma, or Newton's second law for fluids. It's the conservation of linear momentum in differential form, and that yields the Navier-Stokes equations, which I mentioned in the first video of Chapter 4. So as we have been doing so far in the course, we're going to describe the fluid flow with an Eulerian vector field. So our velocity vector v has three components: u in the I direction, v in the j direction, and w in the k direction. So if we take the derivative of this velocity vector, we end up with three components of acceleration. We end up with du dt in the I direction, dv dt in the j direction, and dw dt in the k direction. But we have to note that each velocity component, u, v, and w, are functions of four variables. For example, u is a function of the three spatial coordinates and time. So if we want to get the total acceleration, we've got to use the chain rule. And down at the bottom, I've just considered the x component, so just considering u, the x component of velocity. If you want to get the total acceleration, then you've got to consider the partial derivative of u with respect to t, the partial derivative of u with respect to x, then dx dt using the chain rule, du dy, then dy dt, and du dz and dz dt. So what I've done on the next slide, I think I've just rewritten this. So that's our total acceleration, considering the fact that u is a function of x, y, z, and time. But these components, dx dt, is just the u component of velocity here. So the rate of change of x with time is u. The rate of change of y with time here is v. And the rate of change of z with time here is just the w component of velocity. So now we can make those substitutions and it'll become u, v, and w for those terms. And so making the substitution now our total acceleration, and all we're considering again is the x component of velocity for the moment. So the acceleration in the x direction, the total acceleration is du dt plus u du dx, v du dy, w du dz. And as I mentioned in the introduction, there are sort of two types of acceleration that we have to worry about. One is the local acceleration. That would be du dt for the u component of velocity. And that's, for example, if you have a transient flow. So if the pump is speeding up and you've got the flow rate increasing in time, the velocity at a point is going to be increasing with time. So at x, y, z, at a given spot, the velocity is going to be increasing as a function of time. But then, in addition, you've got these convective acceleration terms that I alluded to when I talked about the Venturi tube. These local acceleration tubes, u du dx, v du dy, and w du dz, are caused by the flow moving into a zone of higher velocity. And you've seen this in, for example, steady flow in a nozzle or in a venturi. The flow enters at low velocity but exits at high velocity. So even in a steady flow, you have accelerations. And those accelerations are described by these convective terms over here. The previous slide, I only considered the u component of velocity. If you take that same idea but you apply it to the acceleration field and to the velocity vector v, whenever I bold something, by the way, just to remind you, just as the text, whenever you have something that's bold, that's a vector. And so if you apply that same concept to the acceleration field, to the acceleration vector, you get this expression here, where I've simply replaced in here, instead of having u, I have the general the three components of the velocity vector. So this acceleration field is denoted in your book as dv dt here. It's this derivative. Now, that's a little bit confusing because it looks like an ordinary derivative. It looks like v is a function of only one variable. Frankly, I don't like the way the white textbook does that. Most other books don't use a lowercase d there. They use an uppercase d to distinguish that kind of derivative from an ordinary derivative. So you'll have to be a little bit flexible and notice this in your book. This kind of derivative where you include the local and convective accelerations is called the material derivative, or the substantial derivative, or in some books the substantive derivative. And so it's different. It's not an ordinary derivative. V is a function of course, three spatial coordinates and time. So you have to keep your eye out for that. It's a little bit confusing in terms of nomenclature, but I think you can get used to it. So now we have the acceleration field, and it's got this total acceleration includes the local acceleration and the convective accelerations here. And what you've got to remember is this velocity vector v has u in the I direction, v in the j direction, and w in the k direction. So if you expand this equation out, and then you just pull off the I direction, the x direction, you pull off the y direction, you pull off the k direction, what you get is the three components of acceleration. These are the scalar components of acceleration in the x, y, and z direction. So acceleration in the x is du dx, du dt, u dt dx, v du dy, w du dz. And similarly in the y direction we have the local acceleration in the v direction, so that's caused by the transients in the flow, and then the convective accelerations. But here now we have v, but the rest of the form remains the same. So u di v dx, v di v dy, w di v dz. And you can see the form remains the same. If you look at the accelerations in the z direction, we have the local accelerations and the convective accelerations, but now we have w in here. It's worth, I don't want to say memorizing, but it's worth using these equations enough that you get comfortable with those forms. Now this next slide, I almost hesitate to mention it. It's really approaching a graduate level discussion of this, but you'll see this acceleration, the substantive derivative form of the acceleration field. You'll see it expressed in vector notation, and the vector notation is shown over here. So it just becomes v di t, where v is the vector, and then v dotted into this upside down triangle, which is the del, and then that becomes an operator that acts on the velocity vector. So remember, this del or gradient operator is I di by dx, j di by dy, k di by dz. So if you imagine v and a dot product of the velocity vector and the del operator, then that becomes u di by dx, v di by dy, w di by dz. And if you operate that, you apply that operator to the vector field v, which has the three components, you recover the longer form of the acceleration expression. I show you this because many books, many papers just write it down in the vector form, and it can be a little confusing if you've never seen it before. Now I'm going to do a couple of examples. We're going to start with example 1 that considers steady one-dimensional flow of liquid in a nozzle. So we're considering an incompressible fluid that enters a nozzle at velocity v1. And the nozzle has length L, has diameter d1 at the inlet, and diameter d2 at the outlet. And we're asked to derive an analytical expression for the fluid acceleration as a function of x, where the x coordinate here is measured from the nozzle inlet. And here, of course, we only have convective accelerations because we're dealing with, it says in the problem, we're dealing with a steady flow. So let's go through the details of this. We start with the general vector expression for acceleration. So here's the acceleration vector, bolded. There's the local acceleration, and then these are the convective accelerations. And it's mentioned in the problem that the flow is steady, the pump flow rate's not changing, so di v di t is 0. We have no local acceleration. You're told in the problem to approximate the flow as one-dimensional, right? So v and w, the y component and z components of velocity are 0. So our velocity vector just has one component, v equals u in the I direction. And so v and w are 0. The derivatives di v di y and di v di z are also 0. So those terms go away. And so our acceleration equation, we only have acceleration in the x direction, and it becomes the acceleration in the x direction is just u du dx. And notice now I've replaced these with full derivatives. That's an ordinary derivative in this case because now our acceleration is only a function of the x variable. So now to get an analytical expression for the acceleration in the x direction, we just need to get an expression for how the velocity varies in the nozzle. And that's pretty straightforward. We can do that using the concepts from the previous chapter. We know the flow is incompressible, it's a liquid, so the flow rate's a constant, VA is a constant. So using V1 and the cross-sectional area at 1, that's got to equal the velocity at any x location in the nozzle times the cross-sectional area at that cross-section in the nozzle. So we can solve for ux. So I just solved here for ux. And we get that it's a1 v1 over a of x, where a of x is the cross-sectional area. Now the cross-sectional area is, of course, pi times the local diameter squared divided by 4. Pi and the 4 is going to cancel, so we're going to have that the local velocity varies as d1 over dx, d of x squared times v1. We can see from the image that the nozzle diameter varies linearly with distance x, so we can write the expression that d of x equals d1 minus d2 over L times x. You can check this is correct because if you put in here x equals 0, of course you recover d1, and if you put in x equals L, you recover d2. If you put in L here, you get d1 minus d1 plus d2, so you get d2. So that's, you can see just by inspection that that linear equation is correct. So now what I'm going to do is substitute this expression for the diameter into the expression for velocity. And so that's what's been done in this next equation. So now we can actually start to evaluate our acceleration because we showed that the acceleration was only convective in the x direction and it's u du dx. So the acceleration in the x direction is u du dx. This is our expression for u. So I've just made the substitution there. So d squared v1 and then d1 minus d2 lx all squared. So you can see that that's been just a simple substitution. And now this term here is du dx, right? So let's just check that derivative. So keep in mind that x appears on the bottom, so that's like x, so that exponent there is minus 2. So when we take the derivative, we're going to have minus 2 times the entire expression here. You can see it, minus 2 d1 squared v1 is over on this side. And then we repeat the bottom, but because we've taken the derivative, that becomes a minus 3. And now we have to take the derivative of the expression on the bottom inside the exponent, and so we get minus d1 minus d2 upon L. So that looks correct to me. Now in the next slide, I think I've made a little simplification here. Of course, we have a minus and a minus, so the minus sign disappears. I've brought the L down on the bottom. So that's just rewriting the expression that we obtained in the previous slide with a little bit of simplification, getting rid of the 2 minus signs to make a plus sign and bringing the L here down on the bottom. Now I can combine terms. We've got the same term here squared and the same term here cubed, so that becomes, this term becomes to the 5th power. I can combine the d1s and the d1 here, becomes d1 to the 4th, and the v1 becomes a v1 squared. And so that's our final answer. It's always good to check the units. It's not 100% foolproof, but it's a good way to check that you haven't accidentally dropped a term. So of course we have d1 is meters to the 4th, and then this term d1 minus t2 is going to have units of meters. Velocity 1 squared is meters squared per second squared. L has units of meters, and this term of course is going to have units of meters to the 5th. And so we can see here that that's meters to the 5th, meters to the 5th, that meter goes with that meter, and we have meter per second squared, which is the correct units for acceleration. I'll end this example just by making a couple of comments. If you look at this expression, you'll see that the acceleration is positive throughout the nozzle. If you try evaluating it, you'll see that the minimum acceleration is at the inlet to the nozzle at d1, and the fluid acceleration increases to a maximum at the exit plane d2. I mentioned previously that this acceleration is purely convective. Since the flow is steady, there's no local acceleration. And the acceleration occurs because the flow is being convected into a region of higher velocity. And just as an aside, we saw in the previous chapter where we were calculating forces from impulse momentum that the acceleration of the fluid through a nozzle actually produces a thrust on the nozzle in the negative x direction. So I'll end with this example. What we're considering here is a hypothetical fluid velocity vector field given by the following expression. So we have the velocity vector v here given by ct x squared minus y squared in the I direction. That's the velocity vector component in the x direction. So this we normally denote as u, lowercase u. We have minus 2c xyt in the j direction or in the y direction. So this we normally denote as lowercase v, plus 3y in the k or z direction. So this we denote as the velocity component w. And so given this velocity vector field, we're asked, is the flow steady or unsteady? Then we're asked to obtain an expression for the acceleration vector. Remember, bolded letters are vectors. And then once we get that expression, we're going to evaluate the acceleration vector at x, y, z, t equals 1, 1, 1, 1, where the units are arbitrary. So we start by considering the issue of steadiness or unsteadiness. Also, another way to express it is whether the fluid
velocity field is transient. And what we notice right away, if you look at these, is the u component and the v component of velocity have time appearing in them. And so that's going to give rise to local accelerations. And so the fact that time appears in just even one of the velocity components tells you that the velocity field is unsteady, or the velocity field is transient is another way to express that.
For part 3, we're asked that given this velocity vector field to derive the acceleration vector. So we're going to do this component by component. So the x component, as we just talked about, is du t, u du x, v du y, w du z, where, and I've shown here that this is u, this is v, and this is w. So now we can evaluate these terms. So what we're evaluating here is du dt, which is going to treat all the other variables as a constant when taking the partial derivative with respect to time. So that's just going to become c x squared minus y squared. Then the next term is u du dx. So I've rewritten u here, right? So ct x squared minus y squared. And now I want to take the derivative of u with respect to x, which is going to become 2 ctx right here. The next term is v du dy. So I've rewritten v minus cx yt there. And now I want to take the derivative of u with respect to y. So that's going to become minus 2y, minus 2y ct, right? So there. And then finally we have w du dz. W here is 3y. And then we take the derivative of u with respect to z. There is no z, so you're going to get 0. And then what I've done on the next line is just simplified this term here. So I brought the 2 out, so that's 2 c squared x, there's a t here and a t there, so it becomes t squared. That's the simplified version. And then I've simplified this term. The minus and the minus give you a plus, so combining the c's and the y's and the t's, we get 4c squared x y squared t squared. That's just the acceleration in the x direction. We now have to repeat this for the y and z directions. So here we go. This is the y direction. Notice the form of there's the local accelerations, there's the convective accelerations. So di v di t, u di v di x, v di v di y, w di v di z. So now we evaluate these terms. Let's check this out. This is v here. So we're going to take di v di t first. That's going to become just minus 2 cxy. Yeah, that's what we have. And then I've reproduced u here. So here's u. That's correct. And now we want to take di v di x. So that's going to become minus 2 cyt. Yeah, that's correct. And now the v di v di y, so I've rewritten v, which is minus 2 cxy t. So that's v here. That's the v component. And then di v di y. So that's going to become minus 2 xt. Yes, that's correct. And then w again is 3y. And then we want to take di v di z. Well, z doesn't appear in v at all, so that gives you 0. And then below here, I've just simplified. This term here is going to become minus c squared t squared y, right? That's correct. And then I've combined, of course, the negative signs become a positive sign, and you get a 4 c squared x squared yt. Yeah, that looks correct too. Now we move on to the z component of acceleration. Again, now we're looking at the local acceleration, dw dt, and now we have w in here. So it's u dw dx, v dw dy, w dw dz. So going term by term, keeping in mind that w is 3y. So if we take the derivative of 3y with respect to t, we get 0. Now I've rewritten u here. U is ct x squared minus y squared, so there's u. And then dw dx, well, w doesn't have x in it, so you get 0. I've rewritten v here, minus 2cy, or xyt. There's v. Of course, that was u. And then times dw dy. Well, dw dy is just going to give you the 3. And then w dw dz. Well, w is 3y. And if you take dw dz, w is 3y, so it doesn't contain a z, so that's going to be just a constant, give you a derivative 0. And so this term and this term will vanish, and you only end up with minus 6 cyxt. So now you've got the x, the y, and the z components of acceleration. You can put them in as an acceleration vector. So this is just ax, a couple of slides back. Ay, if you check back, that's ay. And there's our az in the k direction. So that's the answer in terms of the general expression for the acceleration vector. And on this slide, I've just reproduced that expression at the top. And you're just asked in the problem to evaluate this at x, y, z, t equals 1, 1, 1, 1, right? So you'll see, if you look at this, this is 1 squared minus 1 squared, so that's going to be v 0. So 1 minus 1. And here we have 1 minus 1 again, so that term's going to go away. And you've got 4c, and then all these terms here, 1, 1, 1. So you end up with the 4c in the I direction. And then we do the same thing in the j direction. This term's going to become minus 2c. That's right. And this term's going to go away because 1 minus 1. And then you're going to have 4c squared here. That's going to, because these other terms are going to become 1 in the j direction. And then these terms all become 1, x, y, z, x, y, and t are 1, so you have minus 6c in the k direction. So that's the acceleration vector evaluated at point 1, 1, 1, 1, and that completes that example.